Okay, welcome back to the last session of the day. So in this session, we'll be having 3 talks. And the chair of this session will be Professor Sanjay Singh from IIT BHU. Sanjay, please go ahead. You have to unmute. Sanjay, please unmute.
Yes. Thank you, Seti, and thank you. So this is the last session for today, and we have 3 speakers. So our first speaker is Dr. Chiranjeev Mitra from IISER Kolkata, and he will be talking on topological transport and topological photocurrent in 3D topological insulator. So let's welcome Dr. Mitra. Dr. Mitra, over to you.
Yeah, thank you. So I'll share the screen. Please let me know if it is coming.
Yeah, we can view. Yeah.
Okay, so is it in presentation mode now? The full screen?
Yeah, it's full screen.
Okay, great. Well, let me start first of all by thanking the organizers of this conference, and there have been some excellent talks throughout the day and even yesterday. So I'm going to talk on, so basically on topological insulator thin films. That's what I work on. And there have been a few talks on single crystals. Today, Kaustubh Manna gave a fantastic talk on single crystals. So, my work is based on these papers that I have given. And the 5th one, which has just been published online, is the one on which I'm going to talk most of it. So just to give a outline of the talk, I will rather skip the brief introduction to topological insulator because there has been a lot of introductions already. So I will talk about signature of topological insulators in transport experiments, then a little bit of growth through PLD technique and transport experiments, and then surface to bulk coupling, and that's something which will be important. Linear MR, if I have time, I will speak about it, and then I will talk about some noise measurement and photocurrent measurements, which we did not too long ago. So, yeah, I will skip this slide because a lot of introduction has been given already. I will focus on this, like in a topological or 3D topological insulator. Okay, let me switch on the pointer. Right. So this the conduction band, the bulk conduction band and the valence band is actually interspersed by these surface states, and our Fermi level in an ideal topological insulator lies somewhere in between the conduction and the valence band, so that we have, let's say, one type of carrier only, which is like the surface carrier at the Fermi level. However, this is an ideal scenario, and we will see in today's talk that this is not always the case. And if we go into the momentum picture, so this was taken from Zaid-Hassan's paper. This is the angle resolved spin angle resolved photoemission spectroscopy, where we see that the surface states are on a Dirac cone, and actually there is a strong spin momentum locking as we go around here at the Fermi surface. We see that the spins also rotate. So there is a very strong spin momentum locking, as can be seen here. And this is one of the reasons which is responsible, which is one of the candidates which is responsible for the pi-Berry phase that we have seen quite a bit in this talk. So the criteria for having a Z2 topological insulator is that we need to have large spin-orbit coupling, and that's the reason why bismuth is used. It has to have a band, it must be a band insulator, and there are odd number of Dirac points, which is the topology, and spin texture of the Fermi pockets, which we saw in the last slide. So some of the materials that we are going to study in this talk, actually, which has been studied, is bismuth selenide, bismuth telluride, a mixture of bismuth selenide and telluride, and then we added antimony also to this. So again, this has also been dealt with in many talks. I'll rather not stick to it. Just one thing I want to say is that so this is the quantable layer, and if you see this picture, it's like a hexagonal or triangular structure, and that can be captured from many measurements like AFM and other things also, which we'll see. So this is our pulse laser deposition chamber. This is the laser, excimer laser, and this is the chamber. So the sample that we are going to talk about is Bi2 SC2 TE or Bi2 minus X SBX TE1 minus Y SEY, which is called BSTS, and this is called BST. These are the two major samples. So why do we study these samples? So one of the reasons is that if we see the band picture is that one can easily have the Fermi level lying either in the valence band or in the conduction band. And in that case, there is a significant amount of bulk conduction, which actually kills the purely topological transport. So therefore, we need bulk insulating. And what happens is, in many of the cases, selenium being a volatile material, it actually evaporates and there is selenium vacancy. So in order to, so the selenium vacancy actually pushes the thing to be hold off. So in order to balance it, we put some tellurium and some antimony here. Okay, so that is the reason why we have this mixture to bring the Fermi level back inside near the Dirac point. So basically for a better position of the Dirac point and a better spin structure. So okay, I will skip this. This is a characterization using Raman. So this is the structure that we see of BSTS. So this was the elemental analysis done using EDAX to verify that what we have is indeed what we wanted to have. This is the grains. We also did a atomic force microscope measurement, and you can see this triangular type of structures that of the grains that happens here. And this is the Raman. So Raman and apart from XRT, Raman and AFM were the tools that were used to characterize the samples. So when we measure the temperature dependence of resistance here, we see, so this is a classic topological insulator resistance of the BST thin film, that we see that it is insulating. Okay, so there can be a variance of resistance versus temperature behavior depending on where exactly the Fermi level is. Is it inside the gap or it's actually inside one of the valence band or conduction band, depending on p-type doping or n-type doping. So for that, we studied a variety of samples, and here you can see, even though this is a topological insulator, but the R versus T is actually shows a metallic behavior. And here is another example, just by varying the deposition condition, that we get a purely insulating bulk behavior. Okay, so both of them will have this sort of weak anti-localization effect. So it is inverted because in one case this is delta G, in another case it's delta MR. So both will exhibit similar behavior. However, the coefficients will be different. So that's what we will go into the next slide, is that what is this weak anti-localization, though it has been dealt with in detail, but just it wouldn't harm doing a little bit of that. So basically, so we have this the forward moving let's say path and the backward moving path. So whenever there is a constructive interference in the forward moving path and the backward moving path, we have a weak localization. And whenever there is a destructive interference between the forward moving path and the backward moving path, as it happens in the case of our topological insulator with odd number of data points, is that so basically there is a destructive interference, and that is the reason why we have what you get weak anti-localization. However, when you switch on the magnetic field, we actually break the symmetry, and therefore you have a decrease in conductance, as opposed to the weak localization where you have an increase in conduction when you have the magnetic field applied. So this can be fitted to what is called the HLN Hikami-Larkin and Nagaoka equation. And there are two components to this. One is the logarithmic part and the other is the digamma function. So that is basically given to take care of the singularity at b equal to 0. So yeah, so we will basically, so this is the reduced HLN equation in the low field limit and low spin orbit coupling limit, and B phi is given as h by E L phi square, where L phi is a phase coherence length. So just to see what is the phase coherence length here, see this is basically the phase coherence length. So if we have a forward and backward moving path, so that is the order over which the phase coherence is maintained. Okay, so now coming back to transport properties again, this is the same slide. So let's say we have a metallic sample and we have an insulating sample. Both fitted do give me similar behavior of conductance. However, in order to resolve this issue of metallic behavior and insulating behavior in transport, we actually so if I plot the as a function of temperature, if I plot these two parameters which I had mentioned here, so one is alpha and another is L phi. So if I plot these two here, so for the two different scenarios, so in one case I have seen that the alpha, which is basically the bulk insulating sample, we see that the alpha, so on the right hand side is alpha, left hand side is phase coordinates length, alpha remains sort of more or less similar. However, in this case, we see that it varies with temperature. This is for the metallic sample. So how do we explain this variation in alpha? So for that, we consider, to resolve this issue of alpha, we consider three samples made in different conditions. So one is B1, which is 200 nanometer thick insulating bulk sample, and as B2, 500 nanometer thick insulating bulk, and as B3 is 200 nanometer thick metallic bulk. Okay, so this was just by varying the deposition condition we were able to achieve this. And let's say this is B1. Okay, so just a minute. So this B3 is what is shown here. Okay, this is actually B3. So so what we see here is actually when we have this scenario, we see that in both these cases, the alpha is more or less independent of temperature for a reasonably larger range of temperature. However, for the other case, we see that it grows with temperature. So this is the reason why this happens. So this is that B2 sample is very clear, is that in one case, so what is alpha? Alpha is actually the number of independent channels which basically, okay, so let me just I forgot to emphasize here one thing, is this behavior is actually, strictly speaking, 2D weak anti-localization. Okay, so alpha, so if I have a sample, then we have two surfaces, the top surface and the bottom surface. So ideally, for a very bulk insulating topological insulator, the alpha should be close to 1. However, for a system where you have significantly large number of bulk carriers, the top and the bottom are joined sort of by the bulk carriers, and therefore you will have only one alpha, one surface. Okay, so that is the reason there is a variance. And to understand this, we got this band picture. And this, in the band picture, basically you have somewhere, so we by fitting the data, fitting the R versus T data to an activated behavior, higher temperature part, we see that the parasitic doping gives you defects level somewhere here. Okay, so that is actually in the band picture. So in the bulk insulating behavior, so the transport of the bulk can be mediated by activation from here to the higher excited state. So so that is what we captured here. Okay, and just to conclude this part, I just want to say that there was a theoretical paper which actually gave this scenario, is that if you have, so irrespective of the thickness of the film, the top and the bottom surfaces could be coupled or decoupled depending on how many bulk carriers are there, and the bulk carriers are coming from the doping, or rather the vacancies, selenium vacancies. And if the two states are coupled through the bulk, the top and bottom, then we have only one channel. However, if they are significantly decoupled, either could because you have a large thickness, or you have a minimum number of dopants, then in the bulk, then you have two distinctly decoupled topological surface state. And for topological transport, which I had exhibited, like the bulk has to be insulating, so it has to go like that as opposed to like this. This is the ideal scenario. Okay, so that is what we wanted to capture here. This was also seen through some noise measurements that we did subsequently. So this was done in collaboration with Professor Avik Bid and ISC Bangalore. So we got this BSTS sample, and it was actually patterned, and we had made the structures. These are the gold contact pads. So basically, here also we measured the R versus T, and what we found was basically, sorry, this equation has gone outside the screen. So this is your purely insulating behavior, and there is a deviation from this purely insulating behavior, and there is, as you can see, there is a bending, and you had seen that bending in the other case also, and this bending comes about from the increasing dominance of the surface state, the contribution of the surface states over the bulk, and that's why you have a deviation from the bulk. And this blue dot is actually was fitted to the mod variable range hopping here, and here D is actually 3, so therefore you have a 1/4 type of behavior, and we were able to capture this sort of mod variable range hopping because of those mid gap states. Okay, so the hopping between those mid gap states. Okay, so so this is the random telegraphic noise measurement of the same sample, this sample. Okay, and you can see here. So basically, what we have here is the in the first diagram, the RTN as a function of this is the power series spectrum. So at different temperatures, and when we evaluated the power spectrum density, we plotted them as a function of frequency here, and this straight line is a 1/f line, and here we can see that there is a deviation in certain region from the 1/f noise. To capture this properly, we plotted this as a function of so f times the power spectral density by R square as a function of frequency, and you can see that at these particular temperatures you can see an enhanced deviation from the 1/f type, and this is like a Lorentzian, and this is something which is basically the contribution, which I'm going to come again later, contribution of those impurity sites. Okay, so this is the expression that we had fitted the power spectrum to, and 1/f we split into 1/f and to a Lorentzian, and fc is the characteristic frequency at which this transition is happening. So yeah, so we were able to fit that, and from there we obtained the fc, and fc was plotted as a function of temperature, and we see that there are two characteristic temperature. So one is around 60, 70 Kelvin, and another was around a little less than 150 Kelvin. And when we actually fitted them to the Arrhenius formula, the activated behavior, so we got one of them to be 193 MeV, another to be there were two characteristic frequency scales, or yeah, another to be 84.5 MeV. So that when we plug it back into the basically the band diagram, so they are basically somewhere here. So there are two levels here, and the Fermi level lies here. So basically these are the two defect centers, and this is somewhat, so the noise measurements are also in consistent with previous thing that we did just by fitting the activated behavior of resistance. So there we obtained only one impurity level. Here this is more accurate, and we can see that there are sort of two impurity levels, but they are inside the gap. Okay, so that brings me to the third part of the talk. So so that is basically topological photocurrent in topological insulator, and this was in another topological insulator, which is SP2TE2SE. The reason we chose this sample was because in the literature we found that this has a higher amount of absorption coefficient or higher absorption efficiency of the photon. So to describe this setup, because this is a slightly different type of setup, so this has just been published online, and this was done with my colleague Vipul Pal. So this is the setup basically. So we have the topological insulator sample here, and the photon. So this is the x direction, this is the y direction, and the z is perpendicular to the or normal to the surface of the sample, and the photon was incident in the x z plane, and the photocurrent was measured along the y-axis perpendicular to this plane. Okay, so this is H1 and this is H2. So this is the setup basically. The laser. So this was a laser that was used was 650 nanometer laser using a chopper, which was chopped at a frequency that is measured in the lock-in amplifier, and we also lock the photocurrent with this lock-in amplifier at the same frequency. Okay, and the size of the beam, this lens was used, and there was a quarter wave plate which was basically rotated to vary the polarization of the light, because there's a polarization dependent measurement, and the spot size was about 160 microns. Okay, so this is the helical photocurrent. So okay, so let me explain. So as I mentioned here, that JY, the photocurrent, was measured along the y-axis, so that's why I called it JY, which is basically normal to the incident plane of the light. So so this is measured in nanometers, and as you see, so okay, so what is this angle theta? This angle theta is the angle with which the beam makes with the normal to the surface of the sample. Okay, so this was also varied. So we varied continuously at a rotation of 5 degrees, the rotation angle of the quarter wave plate, and 0. So the 0 of the polarization is actually when this is actually, so this is in the plane, xz plane. Okay, that is 0. So as we vary, so this is, let's say 0, this is 45. So 45 corresponds to left circular polarized light, 90 degree again p-polarized. This is right circularly polarized light, again p-polarized. This is again left circularly polarized light and right circularly polarized. Okay, so as you can see, so this is theta equal to 15 degree, this is theta equal to 35 degree, and this is theta equal to 55 degree. And on the right hand side, we see the same plot, but where the beam is coming from the opposite direction. So basically, if I take this, so let's say this is positive theta. So if negative theta means beam is coming from this direction. Okay, and this measurement was done at the center of the sample so as to avoid any photothermal current. Okay, so one can see that so let's say this is let's say we take the positive theta, so we take plus 55 degrees. So one thing you can see that as we go on increasing theta, basically your current, there is an enhancement of the current, and that is actually understandable because there is better coupling between the when the angle increases, better coupling between the polarization and the photons and the electrons. So what is this? So this is the helical photocurrent, signifies that actually that okay, so let's take the example of theta equal to 55. We can see that for left circularly polarized light, rather the right circularly polarized light, which is 135, is less than the left circularly polarized light, and the same, and here it is just the opposite. Let's say the left circularly polarized light is less than the right circularly polarized light. Okay, so why is there such a difference? And this difference, so I will come to this equation in a moment. Let me just explain the phenomena that is happening. So this was taken from Gedic and Nature Nanotechnology, which was published in the year 2011. Is that, so this is the Dirac cone, and I have this spin momentum locking. So the electrons are like this. So let's say we have equal number of electrons in the surface, which are basically going in. So the thing is, these are, let's say the spin is in this direction and the spin is in this direction. So if this travels in this direction, then this has to travel in the opposite direction. Now, if I am selectively exciting using the circular polarization, selectively exciting, let's say these electrons, okay, because the transfer of momenta for different circular polarization will be different. So let's say I am exciting this, then these are the ones which are remaining, so that you have excess these blue carriers and they will conduct in this direction. Now, in absence of any excitation, we have equal number of spin up and spin down electrons, let's say, and both, so the currents will cancel each other. Okay. However, if you create, like, let's say these are vacant states, then this will dominate. Okay. So this current will dominate. So therefore, you will have a current along the y axis. And when you vary the polarization, you basically excite different types of photons, and that is the reason why you have what I mentioned here, is that for left circularly polarized light you have one type of current, for right circularly polarized light you have lesser number of current, and here it is just the opposite. That is because the momentum transferred is different for when it is coming from this side and when it's coming from this side. How much time do I have left?
You have 3 minutes.
Okay, 3 minutes, quickly. Okay, so this was fitted to this equation, and this component is the one which is called the circular photogalvanic effect, and this captures the circular photogalvanic effect, which is essentially the surface carriers. And these are, so J1 and J2 are actually respond to the linear polarization, and J2 and D, so D is the polarization independent term. So J2 is the one which completely captures the bulk behavior, and JC and J1 capture the surface behavior. However, this captures a circular photogalvanic effect, and this is the surface. This is the linear polarization that comes into the picture. So, okay, let me skip that in time. So, when we actually put this, so this is basically the equation there, and then so this is as a function of theta. Okay, so JC as a function of theta goes as C1 sine theta plus C2 sine 2 theta. JC is the circular photogalvanic part, and then there is surface. So this is circular. This is the surface contribution, but this is basically the part which responds to the linear polarization. And here also the dependence is sine theta, and this is sine theta plus sine 2 theta. There are two components here. One is circular polarization and another is circular photon drag effect. So photon drag effect is that when you have angular momentum and linear momentum basically is imparted by the photon to the electrons. So J2, which has a even dependence, so these are the odd dependence. J2 has an even dependence to theta, and this captures completely the bulk part. And this is the theta independent or theta or phi independent part, which is basically just the thermal part. Okay. Okay. So I'll skip this. So now just the last part, which is when we before we put the beam at the center, now we put the beam at one edge and beam at another edge, so that there is a photothermal EMF induced in the sample. And what we see, so this is, let's say, edge 1 and this is edge 2, and we are coming both from plus theta and minus theta in both cases. And this is the plot, the final plot. And what we see here, let's say we take theta equal to 55 degrees, and this is edge 1, and these are the components basically. So we see, and when you actually, so this is the plus theta 55, this is the minus theta 55. These are the corresponding fits, and we have given 0.1 D because in this case the thermal EMF is quite high because we are putting them at the edge. So that's why it was scaled accordingly. And you can see that when we reverse the angles, the J2 and JC, sorry, J1 and JC actually reverse the signs. And however, these two don't reverse their signs, and that actually tells you that the nature of the origin of these two, like J2 and D and J1 and C, are different. So this is basically the surface part. This is the bulk part. Here also the same thing happens. Now what happens is, in addition, because we are putting at the edge, in addition to, so let us go back to this. In addition to, so let's take this scenario. Let's just take this scenario. I am applying this photon. Let's say this is left circularly polarized light, and S1 is excited, spin S1, which is directed in this direction. So therefore we have excess of S2, and they are moving in this direction. But the thing is, when we are focusing the photon here, there is also a thermo EMF, and these two basically add up. So there is an enhancement of photocurrent. And in this case, it is the opposite. So what happens is, we are exciting, let's say S2, and S1 flows in this. It's the same thing actually. So in the H2, it is just the other way around. So in one case, actually, you have the photocurrent going in the same direction as the thermo EMF. In the other case, we have the photocurrent going in the opposite direction to the thermo EMF. Okay. So, right. So let me conclude. Okay. So this is the H1 and H2. Let's look at this. Yeah. So this, so this is the magnitude. So yeah, the magnitude of photocurrent excited by right circularly polarized photons is lower than that of L near the H1. And the same thing nearest to the magnitude of photocurrent is left circular polarized is lower than the excited by the right circle. And that is because, so this actually is an important phenomenon, because this can be used for many device applications. Okay. Okay. So successful synthesis and characterization of pulse insulated thin films by PLD reduce defect and enhance surface conduction in the as preferred films. The established connection of Dirac fermion dynamics with weak antilocalization just by looking at R versus T behavior. From there, we were able to find out the separate contribution of surface and bulk and weak antilocalization at MR at different temperatures. Explain the mystery behind the controversial value of transfer coefficient alpha. And noise measurement can probe the generation recombination of the surface carrier. These are like the two level systems. That's why we saw the peak. Case due to localized bulk impurities, and topological photocurrent can distinguish between the surface and bulk carriers, and it can be used to enhance the thermo EMF for device applications. Okay, thank you very much. So I would like to acknowledge my students and collaborators. So Radha Krishna Gopal, Saurav Singh, Jeet Sarkar, Shubhadip Manna, Avik Bid, Sangram Biswal, Bipul Pal, and Samrat. Thanks very much.
Thank you, Dr. Mitra, for a nice talk. Now we have time for questions, so we can take 2-3 quick questions.
Sanjay, can I ask a question?
Yeah, please.
Okay, Professor Mitra, thanks for the nice talk. So the photocurrent measurement, so I do not recall like what kind of systems that you are working. Is this time reverse symmetry broken system or inversion symmetry broken system that?
Well, this was a classic topological 3D topological insulator. So, so basically, this is the Dirac cone of so this type of.
So if I want to measure, for example, this white emitter, so do I see something different? I don't know.
Let me tell you one thing. That is in my agenda.
Okay.
So we haven't done it, but that So if somebody can provide me good samples, because I haven't been able to make any wild metal samples yet, so that will be good to study actually. So this is in my agenda, and the second agenda is, so this measurement was done at room temperature. The reason is the sample is actually tilted and moved along the beam. So we would like to extend this to low temperature also. So that is some of the things that we want to do, and to explore wild semi-metals also. Yeah. So that is another thing. Yeah. I haven't looked at.
Thanks.
Okay. Any other question? Okay. So no questions. So I have just a small quick question in the last part. So
yes.
Basically, if we say what is the exact parameter which decides the direction of the photocurrent? Maybe I missed.
Okay. So there are a couple of parameters here, as you can see. So can you see this top equation? So this jy equal to jc sine 2 phi, and the dependence of sine and cos, and then finally d. This d is purely the thermal factor, so dc thermal factor. So which is basically creating the thermal gradient. That is because photon actually heats up the cause a local heating. Okay, so there are two aspects here. So if I go to the experiment here, so you see there are two parameters here. One is this quarter wave plate rotation, which is phi. Okay, so I'm basically varying the polarization of the light, and another is this angle at which it is coming. Okay, so there are some equations which I have not given here. So actually you can see this paper has come online, so we have given them. So the photon couples to the electrons better if this theta is high, because the polarization along the surface will increase if I am actually increasing this theta. And so this is the theta parameter, and the phi parameter, so that is something which I had explained also. So phi parameter is the thing which basically captures this. So if you see this picture, so when I'm coming at different polarization, let's say if I'm coming with linear polarization, then actually what happens is linear polarization can actually be decomposed into equal component of left circular polarized light and right circular polarized light. So it doesn't do anything, okay, to the surface electron per se, like doesn't contribute to the circular photogalvanic effect. However, if I have right circularly polarized light, it will excite one type of spin. When I have left circularly polarized light, it will excite another type of spin. So the direction of the photocurrent will change. Okay. So
okay. Thank you, Dr. Mitra.
Yeah.
So if there are no more questions, so let's thanks to the speaker and
yeah.
go to the next talk.
Sanjay, I have a small point to add here. Actually, we forgot to ask Professor Mitra regarding the talk. So I hope you are okay with that. We are recording your talk.
No, it's fine. It's fine. Yeah, I'm fine. Okay, thank you.
If you are uncomfortable, please do let us know.
No, it's fine.
Okay.
Absolutely. So I will stop sharing.
Yeah, it's important to ask the speaker. Okay.
Okay.
So thank you.
Yeah.
So let's go to the another speaker. So our next speaker is Dr. Subro Bhattacharjee from ICTS India. So, and he is going to talk on enhanced symmetries and topological phases of SU8 Dirac fermions. So let's welcome Dr. Bhattacharjee. And before I forget, so may we have your permission to record your talk?
Sure.
Yeah, thank you. So let's welcome the speaker. Please go ahead.
Okay, let me share my screen. Okay, can you see my screen now?
Yeah.
The full screen?
Yeah, full screen.
Okay, good. So thank you for inviting me, the organizers, and thank you for sticking around. It has been a long day of exciting talks, and good morning, good evening, wherever you are. So I'll be speaking about some of the things that we have been doing in our group recently, and a couple of preprints are long overdue, but we will have them soon. So in particular, I'll be talking about these enhanced symmetries and topological phases of SU8 Dirac fermions, and hopefully I'll try to convince you that these may be relevant to material systems. And this work is mostly driven by these two students, Basudev and Ankush, in ICTS, and also we are collaborating with Vijay Shenoy for this particular work. And the particular set of calculations that I'll try to discuss in the next half an hour or so are due to Basudev, and I'll point out some of the contributions that Ankush have recently provided. Okay, so let me start by a very quick overview to this very advanced audience. Just to point out and set things in perspective. So in quantum condensed matter, the various degree, we start by discussing quantum condensed matter by specifying the degrees of freedom, symmetries, and interactions. But all these different ingredients are essentially effective because they depend upon the energy scale. And this is something that we all are very familiar with. And in the sense of quantum condensed matter, high energy physics, which is at the scale of 1 electron volt or something like that, we have these different elements and ions and electrons. And this is where some of the first principle calculations become extremely useful to provide us with a starting point about thinking about materials. But once we start thinking about low energy physics of the order of 1 MeV or something, which often is experimentally relevant, we often need to think about low energy degrees of freedoms like spins, phonons, magnons, vortices, etc. And in that case, the language of quantum field theories often become very useful. And in this talk, what I'll try to point out is new and hopefully exciting examples of emergence of symmetries and their consequences happening in a class of spin-orbit coupled 2D systems. Okay, so this emergence of symmetries is of course well known, and for example, things that have been discussed over the past 2 days, like graphene, where the high energy physics consists of the lattice model of these electrons, and something like this on a honeycomb lattice has threefold rotational symmetry, but at low energy, we end up with Dirac cones for the electrons, and at least at low energies, we get continuous rotation, which is then sort of broken softly as we go to higher and higher energy. And so, so in a way, this low energy physics is constrained by the microscopics, both the microscopic symmetries and energies. For example, in graphene, the 2 sublattice structure shows up as pseudospins for the Dirac fermions. The time reversal symmetry leads to this fermion doubling on a lattice, and we get 2 valleys. And so the structure of the low energy theory in terms of the degrees of freedom, symmetry implementation, and its energetics are constrained by the microscopics. Similar things often also enhance the enlargement of symmetry and enhancement of symmetry often occurs at critical points of phase transitions, where we get these large conformal field theories which are not there in the microscopic case. Okay, so it is useful to ask, what are these emergent symmetries good for? And in practice, as a theorist, it is often good to understand experiments in the slides. For example, this slightly modified the set of steps, the actual values of steps of integer quantum Hall effect in graphene is very easy to understand in terms of the Dirac fermions. And these low energy field theories allow for controlled calculations, which can then be compared with experiments, low energy experiments. And once we know the starting point, we can ask what are these other terms that are there, whether they're, what are their effects, whether they're relevant or irrelevant, and one can try to use the apparatus of renormalization group to try and answer some of these questions. But in principle, and there is another much more profound, I think, reason to think about these things is starts with the question of how many different kinds of emergent symmetry groups can we have in context of different materials. In the sense that we have microscopic symmetries in materials, and the low energy theory gives rise to quantum field theories with emergent symmetries, and how many of them can arise. And this is important because it helps us to find the structures of phase diagrams of such low energy field theories, which can then be explored in context of concrete materials. And this is something that we are now very familiar with in, I mean, forcefully enunciated by all these topological material databases, etc., that we heard some of it yesterday. Okay, this continuing what I said, these gives rise to concrete understanding of phases and phase transitions in different kinds of systems, and often the novel implementation of symmetries on the low energy degree of freedom are key to get in getting exotic quantum phases. And examples include the topological band insulators, where the time reversal symmetry in presence of spin-orbit coupling is implemented in a way that is not possible without in presence of spin rotation symmetry. More exotic examples include anomalies in condensed matter physics, deconfined criticality, and fractionalizations of quantum numbers, etc., where implementation of symmetry is quite novel. So the relatively recent realization is that the spin-orbit couplings plays a central role in many of these phases. And in the rest of the talk, I'll give you an example of a J equal to 3/2 system in 2 dimensions. And the symmetry implementation, as I'll show, is very different from graphene, even though it is on a honeycomb lattice and gives rise to a rich set of phases and possible phase transitions. So this is a situation of d orbitals in an octahedral crystal field, and the issue of J equal to 1/2 has been explored quite extensively in context of iridates and ruthenates, but an equally interesting and maybe a bit more richer is the case of the quarter field J equal to 3/2 orbitals that can arise, for example, in this kind of compound zirconium trichloride, which one can take as motivation for thinking about these kind of systems, but hopefully there are other materials waiting to be discovered. So the point is that these d orbitals sit in this corner the edge sharing octahedral geometry, and one can the starting point is to think about the electronic band structure, the low energy part of the electronic band structure of these orbitals. And if one constructs the minimal hopping Hamiltonians, one needs to think about the 4 J equal to 3/2 atomic orbitals and implement all the symmetries, and the leading order exchange, the leading order hopping the amplitudes are such that you get these 4x4 matrices RR prime, such that if you go around the hexagon, you get identity. So in general, these are 4x4 matrices, but if you take the product of these 4x4 matrices around the hexagon, you get an identity, which basically means that this Hamiltonian, even though it is not apparent, has a secret SU4 symmetry, which can be made manifest by doing some local transformation of these orbitals. So one can make this transformation and go into a basis where this SU4 symmetry is manifest, but because of this minus sign in front, which cannot be gotten rid of, you get these Ising variables in front of it, such that the Ising variables going around the placket gives you minus sign. And this basically means that I have these degrees of freedom effectively seeing a pi flux going around the placket. So what we end up having is a honeycomb lattice in a pi flux, and one can diagonalize this Hamiltonian and get to the band structure. It has 4 bands coming from this enlarged unit cell because of the magnetic translation group, and which has Dirac points at quarter filling and 3/4 filling. So at d equal to at quarter filling, you have these 2 Dirac points, and the low energy physics around this quarter filled state is dictated by these Dirac points. And the similar case also arises for 3/4 filling. So some of these things that I'll be talking about also applies to this case. Okay, so then we go about constructing the low energy Dirac theory, and in terms of these spinors, somewhat similar to graphene, but now instead we have a 16 component spinor, because I have the upper band and the lower band for the Dirac basis. Then there is an SU4 structure which gives rise to 4 flavors, and then there are 2 valleys. So this is the enlarged spinor that we are faced with. And then we can introduce three kinds of matrices, the 4x4 matrices to keep track of the SU4, and two sets of Pauli matrices to keep track of the valley and the particle hole space. And that's essentially the low energy theory. So we can cast this low energy theory at this point somewhat similar to graphene, but we have these the gamma matrices or the Clifford algebra, which has a higher dimensional representation. And in this basis, this SU4 as you see is all identity, so it's manifestly SU4 diagonal. Good. So that being the free theory, we can ask what is the symmetry. So the symmetry turns out in a straightforward way, you can see that there is, since it's SU4 diagonal, it has an SU4 symmetry, and from graphene there is an U1 symmetry, which is often called the chiral symmetry, which can be constructed out of the two Pauli operators, the valley and the particle hole, which anti-commutes with these gamma matrices. But in actually the symmetry is much larger than this, and it is, and one can check that it is not this SU4 cross SU2, but an SU8 symmetry with 63 generators, which can be obtained by combining the taking direct product of the generators of the SU4 and the SU2. And in addition, there are these emergent Lorentz invariants, etc., etc. Okay, so what are the consequences? So the consequence is that we have this enlarged symmetry at the microscopic at the low energy level, but the microscopic symmetric group is much smaller, and it consists of lattice symmetries and time reversal and so on and so forth. And so what we need to understand is what is the consequence of this enlarged symmetry, SU8 symmetry, on the low energy fermions vis-a-vis the microscopic symmetry. So to understand the symmetry, the symmetry implementation and the approximate phases. So let me try to discuss this a bit more carefully. In terms of the microscopic observables, we have these microscopic electron observables like spin, charge, etc. And often these microscopic observables are related to the low energy field theory observables in some way, which is a linear combination of the field theory observables. And this correspondence basically means that there is this microscopic operator like spin, whose symmetry transformation properties are same as some of the field theory operators that we can define in the low energy level, like this. Okay. So it is in that sense, if I look at these operators in the field theory, I would be able to construct the appropriate microscopic operators and understand their properties in the low energy limit. And what we know are that for these kind of theories, there are two most there are a bunch of field theory operators which are most important, which are these operators which have the slowest decaying correlations, which affect the low energy theory most. And then it's the question then is, what are these slowly decaying operators in the low energy Dirac theory? And it turns out that there are two classes of such operators. One are the conserved currents, which gives rise to Noethel theorems. And these, in this case, constitutes of the microscopic electronic current, because we started out with a theory where charge is conserved. And then since there is an SU8 symmetry, there are SU8 currents. There are 63 of them of this kind. The particular forms do not matter. So that's one class of slowly decaying operators. And the other class of operators are fermion bilinears, which are of two kinds, the scalar operators and the adjoint multiplet. And so the microscopic operators can be written as those microscopic operators which can be written as linear combinations of these things might be important and interesting. And so in fact, it turns out that the conserved currents inside the semi-metallic phase usually are less relevant than these fermion bilinears, and so it is useful to consider only the fermion bilinears to think about the microscopic operators. And there are 64 of them, as I just pointed out. So the idea is that if we turn on interactions, these microscopic fields are the leading candidates to destabilize the semi-metallic behavior in favor of another phase. And then the question is that what are these proximate phases of these free theory when we turn on short-range interactions, for example, like these 4 fermion interactions. And in this case, I'll think about charge invariant interactions like chi dagger chi, which possibly gap out the fermions, and then there are 64 of them. And we also have some preliminary results on the superconductors. In fact, it turns out that there are 72 of them, and I'd be happy to talk about them after the talk. Okay, so what are these 64 phases? Okay, and what we need to do is to try and understand this, the microscopic symmetry transformations of these phases to see what kind of symmetry they break, etc., etc. Okay, and this is involved and at the same time interesting for the following reasons, is that we started out with a pi flux problem. So the transformations, the symmetry transformations are projective, and due to spin orbit coupling, the spatial and the spin transformations gets intermixed. And this leads, this is what leads to the unconventional symmetry implementation on the low energy modes. Okay, good. So just to point out that even things like time reversal or translation, 2D translation, you see that the SU4 part gets intermixed with the spatial part, and this leads to a host of effects. I won't go through all the transformations, but one can check this out to emphasize this point that the spin and the spatial, the real space and the spin space sort of gets mixed up because of the spin rotation symmetry. Okay, and so then the strategy to classify phases is take the singlet or the adjoint and try to think about how these bilinears transform under various irreducible representations of the microscopic symmetric group. And once we have that, we for all the 64 masses, we can arrive at the conclusion as to what kind of symmetries do they break or what are the resultant phases. So, for example, for the singlet and the chiral irreps, which are sort of diagonal in the SU4 space, the singlet irrep is one-dimensional and time reversal odd, whereas the chiral irrep is triplet, which is time reversal even, and this irreducible representation decomposition is already very different from graphene, where the similar set of 4 masses actually divide up into 1 plus 1 plus 2, as opposed to 1 plus 3 in this case. And this is immediately something that one can, an immediate proof that the symmetry is implemented very differently from graphene. So the singlet mass is, of course, the Haldane mass or the Chern mass, and it gives rise to integer Chern insulator, whereas this triplet mass are these 3 stripy charge density wave masses, unlike graphene. And I have drawn one of them where the greens are the positive charge densities and the red are the negative charge densities, or vice versa. And you see that it has this stripy type of pattern. There are 2 other members which are obtained by rotating this picture by 2 pi by 3. So moving on to more complicated masses, and one can think about the similar irreducible representation decomposition of the SU4 under the microscopic symmetric group, and one can work out in these in great detail, the singlet, doublet, and the various triplets, which are odd and even under time reversal. And this is technically challenging, but straightforward in principle, and one can get to different kinds of dipole quadrupole and octopolar orders. And let me just take you through some of them, particularly the topological ones, which are of interest. I just discussed the trivial chiral masses. Let me just move on to this, which are the generalized topological masses, the generalized spin Hall masses, to be precise. And in particular, there is a singlet, which is which instead of the spin Hall effect is an octopole Hall effect, in the sense that in terms of the j equal to 3/2, these leads to octopole currents instead of spin currents, and one can check that if I turn on an electric field, it gives rise not to an electric current like the charge Hall effect, but to a octopole Hall current, similar to the spin Hall effect that we know about. And we have two sets of counterpropagating edge modes. This phase turns out to be a bit more fragile than the Kane-Miller phase, because we have two sets of counterpropagating modes. So we have to preserve some more symmetries than the spin Hall phase. But it is one a symmetric protected topological phase nonetheless. So there are other phases like the weak, the spin octopole Hall masses, which one can work out, and they're more fragile in the sense that they require some lattice symmetries. In that sense, they are similar to the crystalline topological insulators in some cases, in some sense. In fact, these three, the triplets, along with this singlet, form an SO5 subgroup of the underlying SU4 flavor group, and this gives some stability to the if the symmetric breaking terms are weak or irrelevant in the low energy theory, and this of course needs to be investigated further. So one can think about other the Hall masses, but let me just quickly point out to the third class of mass, and in fact point out one interesting case. Of course, in the third class of mass, you get these density wave masses like the stripy octopolar or density wave order and various zigzag octopolar order. People who are familiar with this Kitaev type of magnets would realize that this these are very similar orders in the spin density in the spin channel, which are relevant for the Kitaev magnets. But there occurs one interesting kind of order, which we have four flavors of Dirac fermions, but some of these masses or some of these bilinears do not gap out all of them, but only a subset of them, in the sense that they do not get rid of, they do not completely break the SU4, but breaks it to a subgroup, and the subgroup of SU4 protects some of the remnant Dirac nodes. And these sort of are the density wave semimetals, and so when we want to think about them, it has both broken symmetry as well as gapless fermions. They are like the spin density wave metals, but the semi-metallic versions of them. And one can try to understand some of these features, which I can discuss after the talk. I'd like to end. I have like a couple of minutes.
Yes, you have still 3 minutes. Yes.
Okay, good. That's okay. So let me just point out that this kind of classification provides for the possibility of a remarkable unification as far as the phase diagram and the class of materials are concerned. Is that there are these 64 different kinds of bilinears allow for 64 different kinds of phases, and which have the same low energy correlations to the leading order, and which is only lifted at higher order by higher order terms, which basically means that many apparently unrelated orders or unrelated phase can naturally compete because they have the same kinds of correlations. And some of these, as I briefly alluded to, include competition between symmetry broken phases and symmetry protected topological orders. This is only due to the presence of these emergent symmetry, which can naturally lead to such competing orders. Okay, so that's one point, and this kind of low energy theory actually forms the starting point of various questions, particularly the question of the theory of phase transitions out of the semi-metal in presence of these symmetry or the remnant of these SU8 symmetry that I pointed out. And in particular, in case of such symmetries, we know that once I start gapping out the fermions, the topological defects of these various ordered phases that I land up into carry different fermionic charges, and that can lead to non-trivial phase transitions. And in particular, the proximate quantum spin liquid phases that can be obtained by gapping out the charges can be extremely different, can be quite different from the ones that we know about. And in particular, one thing that one can conceive about is that you start with this Dirac metal, and within a slave fermion decomposition, one can sort of think about gapping out the charges, but keeping the fermions gapless, which can lead to a Dirac spin orbital liquid, and the properties of which the symmetry fractionalization pattern of such liquid is quite different from the ones obtained from lower symmetries. Okay, so with that, I'll quickly summarize that hopefully the D1 or D3 systems on honeycomb lattice with spin orbit coupling are interesting and worth investigating from various points from various points, and this gives rise to spin orbit coupled Dirac fermions with enhanced symmetries. And this point of view is, of course, good for materials where this is weakly broken. And I can tell you some things where some of these symmetries are weakly broken at the high energy level. And this provides a natural starting point to investigate a large class of problems. And hopefully we see more materials for these class of theories. Okay, so with that, thank you for your attention, and I'll be happy to take questions.
Thank you very much, Dr. Bhattacharya, for very fundamental talk, and also you have finished well within time. So thank you very much. And now session is open for a few questions. So from seminar hall, we may start.
No one from here. So
oh, no one. I can see some.
No questions. No questions from.
Okay, no questions from online audience.
There are. You can see there are some hands are raised. So for example, Bangladesh has.
Okay, let me just yes. So yeah, Tanusri, so you can ask. Yeah,
Shubhra, can you hear me?
Yes.
Am I audible?
Yes.
Yes.
Okay. Okay. So my question is, as you were aware, that one of the competing instability is the dimerization. So in your language, field theoretic language of the masses, which one is identified with the dimerization? You did talk about this density wave masses.
Yes.
And there were different patterns of these density waves. So is it like this dimerization of different kinds, like this zigzag or armchair?
Yeah, so I believe that one of these correspond to bond density waves. Okay.
Okay.
And they are related to these stripy the type of orders, and which has the same kind of symmetry that the dimerization the pattern that the initial first principle calculations or seem to find in this compound zirconium trichloride. The question is that the dimerization in the compound, is it driven by electronic correlations as this calculation suggests, or is it because of the structural physics and has nothing to do with electronic physics?
I mean,
so that's
the point,
question.
yeah,
Yes.
that because at least the first principles calculation shows that these are some phonon instability. So then it is coming from the lattice. But whether the lattice basically reacts to the electronic thing, that of course needs to be investigated.
Right. So the point is that these masses actually account for that instability. Sorry, I should have a picture for that. But those instabilities are included in this classification. The question is that the actual instability in the system, as you pointed out, has it anything to do with the electronic correlations?
The other question is it possible from your analysis, because you have this, I think, total 64 masses. So what is the kind of the material dependent parameter in your low energy quantum field theory, so that you can say that, by changing one material to another material, one of the mass would be more dominant compared to others?
That's a hard question, which I don't think I have an answer to.
Okay. Thank you, Shubham.
Okay, thank you. So now next question is from Avdesh. Avdesh, please.
Yeah. Thank you, Professor Bhattacharya, for the very interesting talk. So I have two small questions. One is about this. So as you know, this old paper from Ryu and Shimon and others about the same story, but in only graphene, right? So I think you explained in one of the slides, but maybe I missed it. So what is the relation? So here we are getting many more, right?
Right.
So the difference is coming from the underlying structure, that it has, it's kind of a larger spinner that we are starting with. I'm just trying to understand.
Yeah, so that's one thing. The other thing is that how the symmetries are implemented on these spinors. Okay. So in particular, if I look at this masses, sorry, let me just go through. Just a moment. Yeah. So if I look at these masses, the SU4 is irrelevant because they're diagonal in SU4. But if I look at how these masses transform under the microscopic symmetries, in case of graphene, these four masses were the irreducible representation, the symmetric group has only doublet representations for these kind of masses. And so the four masses break up into 1 + 1 + 2. And this one is the Haldane mass. This singlet is the sublattice mass, which is like the plus minus order. And then there is the Kekule mass, benzene-like mass. Right. Okay. But here what happens is that because you start from spin orbit coupled Dirac fermions, the way the same microscopic symmetries act on these fermions are different. So the irreducible representation is different. And instead of getting 1 + 2, you get a 3, which allows for this charge density wave triplet mass, which transform into each other under various symmetries. So this basically leads to a completely different realization of the same symmetries. And this is, of course, possible because of what you pointed out, the higher dimensional spinor, but also because of the fact that the same symmetries are implemented quite differently in these class of systems.
Okay. And one last question I had was, so for these 64 phases, is it possible to write down tight binding models for these? Or is it
yes, I believe that my student has tight binding model for all of this. I think I'll be happy to share them with you once we are done with this. Which is
yeah, thanks.
Okay, thank you. So, Subra, I have just a small query. So, when you mention these topological defects in order phases, So which kind of topological defects are you referring?
So that would depend upon the kind of mask that I'm thinking about. So suppose I think about this triplet mask. If I do the symmetry analysis, I'll find that the order parameter is a Z3 order parameter. Okay, so then I can think about what are the topological defects, and it has domain walls as well as remnant of the O2 vortex. And then I can ask that if I have such a vortex configuration, Z3 vortex configuration, and I integrate out the fermions, what is the charge because of the at the core of the vortex that's left? At the core of the vortex, the mass goes to 0, so the fermions are sort of gapless in somewhat loose sense. So then some fermions may get trapped, and this core may support for a gapless fermions. And in that case, I'm slightly talking loosely, but this can be made more mathematically rigorous, that the vortex has a finite electronic charge. And then I can ask, okay, so what if I try to think about the dynamics of this vortex, which can then lead to electronic currents? Okay, so these are what are known in high energy physics as Goldstone-Wilczek currents of various kinds. And I think some of it is known in context of various kinds of phase transitions too.
Okay, thank you, Subro. So thank you very much again for a nice talk, very fundamental talk, and be in time. So thank you. So let's thank the speaker, and let's go to the last talk of the day. So the last talk of the day is from Dr. Kenneth Bush from Boston College, USA. And the topic is, the title is Axial Higgs Mode in a Topological Semi-Metal. So again, I would just, from your permission, Dr. Bush, so can we record your talk?
Yes, please feel free. And can you hear me okay and see the screen okay?
Yeah, so we can
Great.
hear and the screen is also okay. So let's welcome. So please go ahead.
Thank you very much, and thanks to the organizers for including me in this very interesting conference. I'm really sorry I haven't been able to participate more, but at this time of day, usually I have to take care of a different topological excitation who can be quite loud. So you may also hear her in the background. I apologize ahead of time if you do. I realize that I'm at the end of the day for most of the participants. So let me just briefly sum up for you what it is we're interested in this talk. So we've heard actually quite a nice set of talks about these topological systems and broken symmetries, and that I'm going to kind of continue with that theme, except that my inquiry is not going to be what happens to the topological states, but rather what kind of new modes can we get when we have this broken continuous symmetry in combination with this topological state. So what I mean by that is, of course, and I apologize, somehow the animations are a little messed up. In any event, that we normally in this Mexican hat potential should get our Goldstone and Higgs modes, or if you want, phasons and amplitudons. But now, to date, all the Higgs modes that have been seen are scalar particles. And what I want to ask is, can we get sort of new emergent particles in these systems where we have this combination of topology and continuous broken symmetry? So in particular, I will try to convince you that we indeed have seen evidence for a so-called Higgs mode, axial Higgs mode, where you basically, this mode is actually of a new symmetry, of an axial representation. So in particular, we've focused on these so-called square net materials. These are quite nice set of materials where you have these square systems where the px and py orbitals primarily sit at the Fermi surface. And as I'll show you, that leads to a natural way to get bulk Dirac or systems. And in addition, it also leads to a nice nesting condition where you get charge density waves. And so this is a very natural place to sort of combine strong correlations and topology. And I'll also show you that it can be a way to get very clean topological systems. So then the question is, of course, how to probe them. And giving this talk, I guess, even if virtually in India. I'm sure I don't have to convince you about the importance of Raman scattering, but that has been our group's approach with this system. Namely, we are, and as I'll show you why, quite interested in Raman scattering for the ability to measure a wide variety of excitations, be they lattice, magnetic, or plasmonic, or let's say electronic, and as well to measure their symmetries and as well as their energy responses. Okay, so when we did that in this particular material with a charge density wave and these bulk Dirac states, we found something quite surprising. So here I'm showing you the Raman response versus energy, and I've colored in the region which is due to the CDW. So you see a few different modes. Some are phonons folded in by the CDW, but the main one I want to focus on around 6 MeV is the so-called Higgs or amplitude mode. And when we measure, as you see in red, that mode by sending light along one particular axis, A prime, and we measure it out along the scattered direction B prime, we see the mode. However, if we simply reverse the orders, so now we send in along B prime and measure along A prime, the mode is almost completely suppressed. And so this was really quite surprising to us, and we couldn't find any example in the literature of this. And we eventually realized that this comes about from a sort of unique kind of combination that happens in this system. So namely, the CDW actually couples two states of, let's say, the same angular momentum, so PX and PX, but it turns out it can also couple two states, in other words, from PX to PY. And when it does that, so basically what will happen, let me just draw it since my animation's got a little messed up here. So you have your PX here, and you also have your PY orbital. Okay, and so now when you excite in the PY, when you excite with an X direction, you can excite to this PX state, but now your CDW will couple you over to a PY orbital, and as a result, your amplitude mode has to have angular momentum. And a consequence of this is in this quantum pathway, you have different phases depending on which way you go. In other words, do you go from PX to PY or PY to PX? The result of which is that when you then combine these two different pathways, you either get constructive interference, which is why we see the mode sometimes, or destructive interference, which is why we don't. And so this really proves that using this quantum interference between these two pathways, we have observed this first case of an axial Higgs mode. I doubt that I'll have time, but if I do at the end, I'll try to tell you about some very recent other results that we've had, where we've looked at the line width versus temperature in a variety of semi-metals. And what we found was that they have this response where the phonons actually, their line width grows very rapidly, but then it peaks and actually, if anything, comes down with temperature. And this temperature dependence is well fit by Fermi functions, which is due to the phonons actually decaying primarily into electron hole pairs rather than into other phonons. And so what this provides evidence for is that in a lot of these topological semi-metals, you have this coupled electron-phonon fluid. So rather than the electrons dumping their energy and momentum into the phonons, which then keep it through phonon-phonon scattering, the enhanced phonon-electron scattering actually means that the two move together and the momentum and energy is conserved for the most part, and this leads to their very high transport mobilities. And if you want more details, I'll point you to our recent publications. Okay, so let's jump right in. So I think, as we've heard a little bit, one of the kind of exciting parts in quantum materials is how can we combine various different aspects. So say topology with various different kinds of orders. And of course, we know that if we take a Dirac semi-metal and we break inversion or time reversal, we immediately create two chiral fermions, or if you want, Weil electrons. And those are quite exciting for various reasons that I'm not going to focus on, as I'm sure you're all well aware. But of course, an ongoing challenge in this field is always how to find the sort of fingerprints of these new systems and of their resulting topologies. I have no time to talk about this, and we've already heard some talks, but my group has done a lot of work on the nonlinear responses, and we recently had an article published in Nature Materials sort of reviewing how nonlinear optics can actually be quite powerful, both for creating such phases and for measuring them. And I'll point you to that review article if you want to hear more. Instead, today, I want to focus on what happens if you have this continuously symmetry broken phase. combined in a topological system. Okay, so in particular, we all know that you'll have this long-range order parameter with its amplitude and its phase, and at the simplest level, we can have some, say, action or free energy, which is written in the Gainsbourg-Landau approach. All right, and so this will give us our usual so-called Mexican hat potential, and therefore we expect that almost regardless of the system, we should see a Goldstone or phase-on mode and a Higgs or amplitude mode, basically a mode in the phase-on case, which is just a sort of sliding of the order, and in the amplitude case, which is an actual sort of optical-like time dependence of the amplitude of the excitation. And of course, this can explain things like, the excitations or the order in an antiferromagnet or an incommensurate charge density wave system. And of course, everyone's favorite, the so-called superfluid or superconductor. Of course, in this last case, actually, you have this problem about wondering about gauge conservation. And it was noticed by a number of people early on that of course, if you couple to the electromagnetism, then this last term in the action will be modified. And as pointed out by Nambu, this is actually how you save gauge conservation, because the phase-on mode basically does it. But the key point is that Anderson then pointed out that this results in your Goldstone mode being pushed up to the 2 delta, mainly because this phase-on becomes sort of a plasmon, if you will, in the superconductor. So he had pointed out there might be connections to high energy. Then shortly thereafter, a number of people, including Higgs, sort of wrote down various simplified models that were very similar to this to try to couple to the standard model, and showed that in fact would give you these massive particles that explain their absence of massless particles in high energy. And as I think everyone knows, this then took another something like 60 years before it was confirmed. Okay, but nonetheless, Higgs himself pointed out that an essential feature of his theory is the prediction of this incomplete set of scalar and vector bosons. And in fact, extensions of his theory to high energy have pointed out that this Higgs doesn't have to be scalar. If you have additional symmetries being broken, it could certainly be a vector case. So condensed matter has been one of the most fruitful places to find such modes. The first example was actually niobium diselenide measured by Raman, where a Higgs mode was seen due to the coupling of the superconductivity and the charge density wave. It would take another roughly 30 years, actually 35, before this would be seen in a just standard superconductor by nonlinear optics, mainly because here what they did was they shine strong intensity terahertz, and they see this in the superconducting state, this nonlinear third order response, which is really coming from the Higgs mode itself. Okay, but nonetheless, all the observations to date, despite, 60 years of the theory, have been of, as I said, these kind of scalar Higgs modes. And so one thing you might ask is, if you really do have multiple symmetry breakings or multiple capabilities, can you see an axial mode? And just as a reminder, what we mean by that, right, is something like a pseudo vector or an angular momentum, where if I apply the mirror, it flips sign. So, it's a pseudo vector in the sense that it's odd under a mirror or time reversal, but is even under 180-degree rotation. Okay, so now I just want to briefly tell you about the systems where we've gone looking for this. So we've been quite excited about these square nets. So if you have px and py orbitals on this square lattice, you can, with a simple type binding model, show that you expect a variety of Dirac points. Some of them, these bulk Dirac points, are not really protected by any symmetry. They show up sort of somewhere in the zone. But there's actually 2 others that are at the zone boundary and will be protected by non-symmorphic symmetries. Another nice aspect of these systems is that you'll find that they have a variety of nesting. So here I'm showing the Fermi surface cartoonishly, admittedly, for the px orbitals. And it turns out there's extra copies here, which have to do with details of the lattice I'm not going to get into. But nonetheless, you also have your py's. And it turns out that, as you can see, there's a nice nesting vector. And because of the small orthorhombicity in these systems, you'll get a charge density wave along with these bulk Dirac like responses in the system. Okay, however, an aspect that was mostly missed in the literature up till now was that there's also a reciprocal lattice vector, that if you take the reciprocal lattice vector and subtract off the CDW, you find that it will couple you not from two states of the same orbital angular momentum, but two states of different orbital angular momentums. In other words, from px to py. Another nice aspect of this series, which has been investigated by Ian Fisher's group extensively, is you can replace the lanthanides with different rare earths, and you can actually tune quite extensively the energy scale of the CDW, and you can even reach a regime where you get two CDWs in sort of in the two perpendicular directions. And recently, Leslie Shoup, our collaborator, has shown that if you go to the lanthanide TE2 series and you dope with antimony, you can actually dope straight to this bulk Dirac point, and the CDW then cleans up, gets rid of all of the trivial bands that you're not interested in. However, for the rest of the talk, I'm going to focus on the LNTE3 series. Our work on LNT2 is ongoing, but nonetheless, they're still quite interesting. Okay, so why have we turned to Raman? I think it's really a post-pandemic tool. As you may know, after the last pandemic, Raman traveled to the Mediterranean, which is when he got the idea for Raman scattering. And in some sense, the idea, it's not what he originally proposed, but what he later used to explain it goes like this. Whenever we have AC light, we should think about an induced polarizability. And I can always expand that polarizability by its coupling to some operator times the fluctuations of that operator. So this first term is the one we're used to. It's absorption or reflectance. It's really the second term I want to focus on, because now I have this noise term multiplied by my AC excitation. And so that's really what generates the sidebands, which we will call Raman scattering. And of course, because we have this tensor, we can then use it to access all the symmetries, right? So not all, to access the symmetry of our modes. Okay, now the thing that's most natural, of course, is that the polarizability is coupled to the lattice, and therefore this is how we see phonons. However, if you have strong spin-orbit coupling, you can actually use Raman to see magnons or spinons, and indeed my group has used that to show the fractional excitations in ruthenium chloride, namely that if we measure the Raman intensity versus temperature and energy, that the temperature and energy dependence is entirely governed by Fermi statistics. However, for this talk, I'm not going to talk any more about magnetism. I'm going to focus on things like the density, which is basically how you see electronic fluctuations. And for example, Raman was used to measure the D-wave gap in the cuprates, and even measure, for example, the nodal versus antinodal behavior by using selection rules. A perhaps far less well-known aspect of Raman scattering is you also have access to some quantum information. So namely, by using polarization and under certain circumstances, it's been known since the 70s that you can actually select out and get interference between different quantum pathways. And in fact, this is actually quite crucial to the Raman scattering in graphene, for example. So I realize this is a fairly complicated slide. So just to sum up, basically my students take a laser pointer, they shine it on a material. Every so often photons will scatter either and create a phonon, a magnetic excitation, an electronic excitation, and I basically tell them to stay there until we see what we're looking for. However, this is, it turns out that these measurements can be more surface sensitive than you'd imagine. And so one thing that we have done recently is to build up a system where we can actually couple in through a vacuum suitcase. So we can prepare samples in a glove box, cleave them, get a nice surface, and bring them in. And in this work, that actually turned out to be quite crucial because GDT3 is a very air sensitive material. So when we exfoliated it and capped it, and then transferred it in air to our low-T Raman, we found that it had a variety of these tellurium oxide modes. However, if we just exfoliated it and then vacuum suitcased it straight over so it never sees air of any kind, we could completely get rid of that surface contamination. And so for the rest of the talk, I will show you data that results from that kind of transfer. Okay, so what did we actually see? So this is a picture of the exfoliated GDT3. We actually did this in a number of exfoliated samples. And we worked with Judy Cha's group, who was able to figure out that the sharp edges that we see in the exfoliated pieces are always the so-called A prime or B prime direction. So then we measure the Raman response. This is actually measured at low temperature, but what I'm going to tell you survives up to high temperature. So here we're sending in data along the b-axis. We're sending in light along the b-axis, measuring along the same b-axis. And as similar to other groups, we see this low energy Higgs mode and a series of phonons that are folded in by the CDW, as well as just standard phonons that are there in their normal state. If we rotate the crystal, and that's actually one thing that we can do in our setup effectively, is rotate the crystal and measure the response. What you see is, as you'd expect, some modes are enhanced, some are disappearing, and that the amplitude mode is sensitive to the direction of polarization. And indeed, if you keep rotating, so now you're going in along A and coming out along A, you see an even further enhancement of the Higgs. This is not terribly surprising. This had been seen before and just has to do with whether or not you're polarized along the Q of the CDW or perpendicular to it. The surprising part came when we measured the cross-polarized response. So here I'm sending in along one axis and measuring out along the perpendicular axis. Okay, so in red, I went in along A prime and I came out along B prime. And this is at 45 to the CDW. And there we do see the Higgs mode and a series of other phonons. If we rotate by 45 degrees to AB, so we send in along A and measure along B, then we see that the Higgs mode is somewhat suppressed, though not fully. But what was really surprising is when we rotated by 90 degrees, so now I'm coming in along B prime and measuring out along A prime, the Higgs is almost entirely suppressed, but all of the normal phonon modes are unaffected, which is what you would expect, right? So basically, again, I send in along one axis, A prime, I measure along a perpendicular axis, B prime, and I see the mode. If I simply reverse the incident and outgoing polarizations, suddenly the mode disappears. So to be sure we really understood this, we went and very carefully measured the angular dependence. And what I'm going to plot for you now is the angular dependence of the intensity of various modes. In red, where they're measured co-parallel and incident and outgoing, and in blue, where they're measured perpendicular. So incident and outgoing are 90 degrees from one another. Okay, so this is what we saw for AG modes. So they basically followed exactly what you expect from group theory, namely that they have this fourfold rotation. They peak when we're aligned with a specific crystal axis, and in the cross-polarized, the fourfold is rotated by 45 degrees. In BG, we see something similar, except now it turns out the BG modes are rotated by 45, so they sort of have nodes, if you will, in their response where the AGs have peaks. This, again, is nothing surprising and follows exactly with group theory. However, if you look at the amplitude mode, what you see is this twofold response in XX. That, again, was not surprising. That was expected. But what was surprising is if you look at XY, is you also see a twofold response. In other words, as I showed you before, if I go in along one direction and come out along the 45 direction, I see the response. But if I rotate by 90 degrees, it's gone. So how do we explain this? So let's go back to the Fermi surface. Right, and remember that there's this QCDW that can couple from PX to PX. Okay, and so what will happen in this tetragonal system is if I send in light aligned with the PX orbital, it will excite from the PZ to the PX. The CDW will take me over to another PX, and then I'll come out with light polarized exactly the same as what I sent in, namely X. And it turns out that this will give you a fully symmetric Raman response, which will essentially look like an AG mode. All right, now there's this other pathway, if I account for the reciprocal lattice vector, where I can couple from the PX to the PY or vice versa. So now if I send in light polarized along this X direction, I excite to the PX orbital. The amplitude mode will take me into a PY orbital and I will come out along the Y direction. And there are two implications of this. The first is that this would give me a response in cross-polarized. But the more important thing is because it has angular momentum, this will give me an anti-symmetric Raman tensor. And this is a well-known thing from the 70s. But basically, if my excitation is axial, then I must have a Raman tensor that's anti-symmetric. Now, since we measure intensity, normally this phase doesn't show up. But in our case, we have these two possible pathways. So in one case, when we rotate 45 degrees from the CDW, what we're doing is essentially measuring RAA plus RAB and getting constructive interference. If we rotate 90 degrees from that, we're now measuring RAA plus RBA, but because it has the opposite sign, we get destructive interference, and that explains this kind of twofold behavior that we saw. And so it's really this quantum interference between these two pathways and this antisymmetric component that prove that we have this axial Higgs mode, which, as I said, has never been seen before. What's even more amazing is this all survives up to room temperature. And we've now seen it in not only multiple GDT3 samples, but also in lanthanum telluride, and also even in someone else's Raman setup with a different excitation laser. Now, if we're getting quantum interference, there's always this, of course, subtlety, that the interference should occur before I square to get the intensity. In other words, I should really be seeing this as the sum of two Raman tensors, and that's indeed what explains our data. It turns out that there are other phonon modes that are nearly degenerate, but of different symmetries. And when I say nearly degenerate, I mean that they're separated in frequency by a little less than, or a lot less than their broadening. So in the data, they show up as essentially one mode. So this is the rotation dependence of the intensity of one of those modes. That was a little bit confusing because you don't see anything that looks exactly like AG or BG. So just to show that a little clearly, this is what you would expect for, say, an AG mode, and this is what you'd expect for a BG. And what we found is that if you simply add the intensities expected for an AG and BG mode, you can perfectly explain the rotational dependence. And so again, as you'd expect, as we all learn as young people in physics, right? When you have interference, it's the sum of the individual components before squaring, whereas if there is no interference, you sum the intensities. And that's exactly what we see all in this one system, again, confirming that we indeed have observed this axial Higgs mode. So just in my last few minutes, I just want to briefly tell you about some other work we've done in topological semimetals. In this, I'm going to tell you some insights that Raman gave us into the coupling of two particles to form a unique fluid, which is a topic I'm sure you're very familiar with. So one of the mysteries in this field since basically the beginning is that if you measure the transport properties of, say, cadmium arsenide, a bulk Dirac system, you find that the transport mobility is orders of magnitude better than the single particle scattering. In other words, the single particle scattering is far, by orders of magnitude, faster than the transport one. And it turns out the same thing is seen in tantalum arsenide and niobium arsenide, et cetera. So one of the explanations that might be given for this is to say, look, in a normal metal, you have lots of density of states for scattering. But of course, in these linearly dispersive systems, you dramatically reduce the phase space. The problem with that argument is, of course, it's true both for transport and for single particle scattering. And so it doesn't really explain their difference. There's also been arguments about, could you be protected by some sort of symmetry? Again, that might make, say, factors of 2 difference between the transport and single particle, but it's hard to see how that gives you orders of magnitude. Similarly, for arguments that you might make about the topology. But what's worse is the data also argues against that. First of all, cadmium arsenide has inversion symmetry. Tantalum arsenide does not. One is a Dirac, the other is a Weil semimetal. But the same result happens in WT2 and in WP2, which are both type 2 Weil semimetals. So it really seems like the specific kind of topology doesn't really matter too much for whether or not you see this. So we decided to look carefully at the phonons, and as I'll try to convince you, they seem to be crucial in understanding this. So normally when you measure temperature dependence of phonons, they decay into other phonons, and as a result, you'll see a Bose factor. So basically, your line width versus temperature grows just continuously due to this bosonic statistics. However, in these materials, we found that there are a number of modes where instead of seeing this anharmonic decay, you see this rapid rise, a peak, and then it comes down. And this is entirely explained by the difference in Fermi functions. And whenever we see that, we always see that this phonon-electron scattering far surpasses phonon-phonon. So in particular, what's happening is your phonon is coming in and it's exciting, say, across the node or within a single band into an electron hole pair. And so it's primarily decaying into fermionic particles, and that explains its temperature dependence. And I'll just say very briefly that we've also seen this now in WP2, the type 2 Weil semimetal, and niobium germanate, which is another type 2 Weil. And all of these materials have different crystal structures. So there's a long-winded way of saying we believe what's going on is we've shown that the phonon-electron scattering is quite substantial over phonon-phonon. And as a result, you have this kind of coupled electron-phonon fluid at low temperatures, which is why you have this very high transport mobilities and very short single particle lifetimes. And we'd love to hear ideas that people might have of sort of new things we should look for in such systems. Okay, so let me just wrap up. Thank you for your attention. I want to especially thank the people who made all this happen, specifically my grad student, Yiping Wang, who's now looking for a postdoc and did the work in the CDW systems. Gavin Osterhout, a former student who's now at Thor Labs and is did the work in the semi-metals, as well as Vincent Plisson. I want to thank various funding agencies, Leslie Shoup for the GDT3, lots of theory help from Prina Rong and Di Zhao, the TEM done by Judy Cha's group, the semi-metals that we measured from Nini and Claudia Felser. And I'll just mention that I'm looking for a postdoc, so if you're interested, please get in touch. So just to summarize, I hope I've convinced you by combining these topological semi-metals with continuously broken symmetries, we might see new topological excitations, that the square nets and Raman scattering are a nice way to look at all this, and that via quantum interference, we've observed this axial Higgs mode, and we are, of course, going to look for other topological excitations. So with that, thank you very much for your attention.
Thanks a lot, Kenneth, for a wonderful talk, I would say, at the end of the session and end of the day, and letting us know about it's very simple technique, but we can do a lot of physics using this Raman. And now session is open for questions. So let me see. Yes. Yeah, so Sudiptoda has question, please.
My question is the presence of axial Higgs modes. This is related to the CDW. I mean, it is only there in the CDW phase, or the CDW is helping you to identify them, and it is already there in the non-CDW phase also.
That's a good question. So maybe I went a little too fast. So basically, the Higgs mode is an excitation of the CDW itself, right? So it's really, let me go back here. So it's really, oops, sorry, I'm in the wrong part of the talk. There it is. So the Higgs mode is really this excitation of the amplitude of the order parameter, right, as a function of time. So if you want to think about it in the CDW, you can literally think of it as like breathing of the amplitude of the wave, of the charge density modulation. So we only can see this as a result of the CDW, not even as a result. It is an excitation of the CDW. So that's what I actually find so exciting, is that it's not sort of baked into the electronic part. It's really, that's not exactly right, but it's basically an excitation of this new correlated state. I hope that
the CDW in these systems are normally incommensurate. So,
correct. Yeah.
So does it have a consequence with respect to other systems where the CDW is commensurate?
In principle, no. So in principle, that's a very good question. So in principle, the commensurability is primarily going to affect things like the phase mode, the Goldstone mode, and also sort of like your ability to depin it. Really, the crucial thing here is that the CDW couples you between states of different angular momentum, right? And the fact that it's in this topological semi-metal, I think, is related in the sense that, of course, that's the same way in which you get this Dirac point, right? Is that you have these different angular momentum states that are overlapping.
Mm-hmm. And has anybody shown this, that these are really Dirac points that you are showing here?
Yeah, good question. So I would say yes. So, well, I don't know what you mean by really Dirac points, but
I mean, calculation of the Berry curvature.
Oh, I see. Well, in fairness, because they're Dirac points, you don't, your net Berry curvature would be 0, right? So you do have inversion and time reversal. So in fact, one of the things we're interested in is, can we tune these systems to be Weyl-like? That would, of course, be very exciting, but we're not there yet.
Okay, thank you.
Okay, thank you. So, so anyone from online audience or from the seminar hall? Oh, okay. So Phil has a question. Okay, please.
Oh yeah, thanks, Ken, for a beautiful talk. So just on this topic that you were just saying, then, with the coupling of the different states, do you mind going back to your Fermi surface sketch?
I do not. Assuming Zoom lets me. Hold on one sec. Sorry. This is always the challenge with making all this work. Let's see. Okay, so I think you are referring to, probably it's easiest here, this one.
Yeah, perfect. So I guess I'm wondering about the second wave vector that you identified between the px and py states.
Yep.
So what's happening at those crossing points? Are these protected by some symmetry in the system? I mean, it looks like even with that second wave vector you've drawn, there's already kind of two processes, px, py, where you could imagine some sort of interference.
Yes, so you have caught on something that I admittedly hid under the rug, but it was also quite interesting. So it turns out that, okay, so let me be a little bit careful. So when you turn on spin orbit coupling, it turns out that these states actually gap out a little bit.
Okay. That
gapping out happens in the normal state and is relatively small, I would say. But another interesting thing that happens is that for example, these don't, as far as I know, but I actually should double check that. Actually, they might. I've forgotten now that I think about it. But the more important part, which gets back to your question, is that actually the CDW gap, this remains a metal. So what you actually have is you see a CDW gap here, and you see a CDW gap here, but you do not see it gapped here, right? So if I were to plot the CDW gap, it almost looks P-wave-like.
Mm-hmm.
Right? Now, of course, how to measure the phase of a CDW gap, I have no idea, right? So I'm not going to actually say that it's P-wave as opposed to plus and plus, right? But nonetheless, you have a node for sure in the CDW gap. Anyway, maybe I've slightly over answered your question, but I hope.
Yeah, no, but that was very helpful. Thanks. Yeah, this is really nice.
Thank you.
So any other questions?
Yeah, so in tungsten diphosphide, you showed that electron-phonon coupling is very important. So is it also related to the cyclotron mass there? Because we see that the cyclotron mass is unusually very high there, 1.5.
Yeah.
It's normally not the case for these high mobility samples. So do you have?
Yes, that's an excellent question. So we're actually working on another work right now related to that, but let me go to that slide because the short answer to your question is yes. Let me give a slightly longer answer, which is not in this PRX, but if you look at our recent Nature communications with Fazal Tofty, if I can get there, sorry, it should be here somewhere. Yeah, so niobium germanium 2, so Fazal did very nice DFT work, and what he shows is that in this system, the masses are enhanced over DFT. I think by a factor of 3, nothing enormous, but large. And so we argued that that is indeed coming from this strong phonon-electron coupling, or electron-phonon coupling, if you prefer. But we are now working on a sort of series of systems where we can see this phonon, basically the band structure is very, very similar, but you can tune on and off this phonon-electron coupling, and you see indeed that the masses are enhanced when the phonon-electron coupling is enhanced. And as of course, at the same time you see, maybe not of course, I should say at the same time you see enhancements in superconductivity. So that's kind of a work that I'm not ready to show yet because we're still wrapping it up. But anyway, if you want to read about masses and this effect, just take a look at our recent Nature Comp paper.
Thank you.
Yeah.
Thank you, Ken. So any other from seminar hall?
No more questions.
No. Okay. So thanks a lot, Ken. And I request all to thanks the speaker. And now, Seti, it's over to you.
Thanks, Sanjay. Thanks for chairing the session. So let's also thank all the speakers of the day for making today wonderful excellent talks. And also thanks to all the chairs who chaired today's sessions. So just before closing the concluding this day, so a small adjustment was there, like rescheduling of Professor Mandar Deshmukh, who was supposed to give on first day, he will be giving tomorrow's first talk. So please keep in mind that. Apart from that, everything is same as per the scheduled plan. Okay, then with this, I think we will conclude for the day. Then let's meet tomorrow. 10 a.m. Indian Standard Time.